And next, we're going to talk about your critical angle. So before we go into what is a critical angle itself, the very first thing we need to ask ourselves is, now, normally when we travel from more dense to less dense medium itself, we normally will speed up and bend away, right? So if you notice this one over here, you do have angle I here and angle R here, right? Now what happens if I were to increase angle I to here? If I increase angle I to here, you also notice that your R will also increase further down, right? So what happens if I keep constantly increasing I, increase until you notice that your R is now 90 degrees. This specific I is what we call your critical angle. So your critical angle, by definition, is the one below here. This one here is the angle of incidence in your optically denser medium, in this case water, which the angle of refraction is actually 90 degrees. So basically, my light ray will travel in this way, and then it will actually go 90 degrees along the surface itself. Okay, so your critical angle itself, you can actually form the equation n equals to 1 over sine c. Now, if you remember, we normally use your sine I over sine r, right? Where on top should be the bigger angle. So if you go and notice this, it's actually sine r over sine I, because we are moving from more dense to less dense. Remember, the bigger angle is always on top. So if you were to actually just press the values sine 90 over sine c, you realize that sine 90 is actually 1 over sine c. That's why we can actually write that the formula is n equals to 1 over sine c itself. So basically, it's actually same as your sine I over sine r formula. It's just that this part you need to take note is that if you want to use critical angle itself, the one on top should be 90 degrees, which is big angle over small angle itself. Okay, then there is another special phenomenon called total internal reflection, right? What's so special is, if what happens when we are at I is critical angle, which is I is 90 degrees, right? What happens if we continue to increase your I further? So if we continue to increase I further itself, you actually realize that the light ray actually, instead of refraction, they actually undergo reflection instead. So reflection, what is the law of reflection itself? Your angle I is equals to R. And in this case, I is actually greater than C. So this is what we mean by total internal reflection, which means all the lights will be reflected into the medium itself, and there is no refraction that occurs. So going back to this point over here, which means that when you're actually very close to your critical angle itself, you can actually have both reflection and refraction itself. So I think some of you have actually noticed this in your day-to-day life itself. Sometimes when you are inside the bus, you can look outside the scenery, and sometimes you do see a little bit of reflection inwards into the inside of the bus itself. So basically, that is your incomplete internal reflection. But once I is greater than C, the word total basically means all the light rays will actually all be reflected inwards itself, and therefore all of them will be reflected. There is no more refraction that occurs. Okay, so do take note, the key thing for total internal reflection is these two parts here. Number one, you must travel from optically denser medium to optically less dense medium over here. So this part. Okay, and angle I must be greater than your critical angle. Now, for your critical angle itself is a bit special. Critical angle is usually the same for the material. So usually if you have glass is always 1.5. Because the formula n equals to 1 over sine c, right? Because your c is always the same for the same material like glass, your c will therefore always be like a fixed number itself. So it's kind of like your density. You have the same medium, you have the same density. Same thing in this case, if I have the same medium, glass, water, diamond, whatsoever, I typically will have a specific critical angle itself. So the angle of incidence and the critical angle is not always the same. Okay, the angle of incidence is what the question gives you, whereas critical angle is something that you can calculate or they will actually give you in the question as well. So do take note about all of this. So total internal reflection is a bit different. You actually will have your light rays bouncing inwards like this. Okay, so let's take a look over here. First thing you want to solve is your critical angle, right? Where you have a refractive index. So first thing, let's write down the formula. N equals 1 over sine c. You want to find c, right? So we just rewrite the formula into 1 over n. Okay, I jump a step there a bit, so you can actually just rearrange this where it is sine c equals to 1 over n first. Then if you want to find c, all you need to do is take sine inverse 1 over n, and you can solve accordingly. So 1 over 1.9. Now, if you all actually notice and you all are familiar with it, you will actually realize that this c is not the speed of light in medium. Do take note, because some students actually confuse them a bit. This c is your critical angle. So some schools, they don't write it as c. Some of them might write it as your theta itself. Okay, so do take note, and then we solve in terms of 1 decimal place, which is 31.8 degrees. Okay, the next one over here, you have your light rays. This is water and this is air. Do take note. Now, for this one, first one, I is greater than c, and for the second one, I is less than c, and this one is your I is 0. Okay, so what happens is, how will your light rays travel? So first things first, you always want to identify the normal. So the thing is, this is a bubble, right? So if this is traveling at 90 degrees over here, the right in the middle, this is your center of the circle. So if you want to draw your normal, all we need to do is draw straight lines, and we will just make it dotted accordingly. Okay, remember, for a circle itself, the normal is the radius. So you do the same for the other side as well. You just do here, 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 and here accordingly. Okay, so now that we have your normal, we can find that this is angle I, and this angle I is greater than c. So we will have a angle of reflection that is equals to I as well. Then for this one over here, because what happens is I is less than c, when I is less than c itself, what happens is that your light ray will actually undergo normal refraction. So ask yourself, you are traveling from optically denser water to optically less dense air, right? So what happens? You speed up, you bend away from the normal. So you will bend away from the normal itself. And what happens? You touch a brand new corner, right? So you draw a brand new normal itself. And then ask yourself, now I'm traveling from air to water. I am gonna slow down and bend towards the normal itself. So you actually end up with something like this. Okay, where I and R over here will be the same as the one in front, because this is actually symmetrical if you realize it. Okay, so this is how you're actually drawing it. So if you need to, you can just explain why. So for number one, ray number one, the one on top, right? So for ray one, when the light ray, as the light ray, or you can see that the angle of incidence is greater than the critical angle and the light ray is traveling from the optically denser water to optically less dense air, the light ray will undergo total internal reflection. So you want to briefly just mention your two conditions, and what will happen is you will have total internal reflection itself. Okay, your two conditions in front, and then what happens afterwards. Alright, the next part over here for ray number 2. So what happens for ray number 2 is when the light ray travels from optically denser water to optically less dense air, the light ray will speed up and bend away from the normal. When the light ray exits from the bubble into water, from the air bubble to the water, right? Because you already mentioned which is optically denser, which is optically less dense. You don't have to repeat so many times. You can just mention that the light ray will then slow down, and bend towards the normal. Okay, so basically there's two steps for this question itself. Okay, step 1 is when you first enter itself, and when you exit is afterwards. Then for ray number 3 itself, what happens is no refraction will occur when the angle of incidence, or we can say that when the light ray is perpendicular to the surface. Hence, the light ray will travel in a straight line. So therefore, nothing happens, it will just travel in a perfectly straight line itself. And this is why you can explain each and every reason why they take the path that you see on top over here. Okay, so it is a possible question that they ask you to draw, and it's also a possible question that they ask you to explain as well. So basically this question itself, right, you can see number 1 is what happens when you TIR and how do you explain it. You state your two conditions and you talk about TIR. And number 2, when you go in and when you go out, basically you are actually two different processes itself, where you travel from more dense to less dense, and as well from less dense to more dense. What happens? You notice that you always want to talk about speeding up or slowing down. You want to talk about bending away or bending towards the normal itself. As long as you travel from A to B, you always talk about these 3 points. From A to B, speed up, slow down, bend towards, bend away. Always need to have these 3 parts. Then for ray 3 itself, because your light ray, not angle, light ray is perpendicular to the surface, no refraction occurs, you just travel in a straight line. Okay, so do take note about all this. These are all the key explanation for all the refraction or all of your light itself. Alright, so now, what's the point of your TIR itself? What's the point of having your total internal reflection? Number 1, it is actually to save space. Because of the binoculars itself, if you notice over here, right, you are actually using this to save space. Because if you don't have the binoculars itself, you actually would need to draw a straight line. So basically, you can just imagine this part being elongated into a straight line itself. You'll notice that it will actually be much bigger than you should be. Okay, and likewise, if you compare this is using a mirror, this is using a prism itself. So prism uses TIR, and the mirror itself just uses normal reflection. So basically, if you compare these two itself, this fella here is fragile. Because compared to a thick prism itself, you notice that over here, right, if you draw normal, 1, 2, 3, 1, 2, 3, I and R is the same. So because it's a thick prism itself, it's not as fragile, and therefore it is actually more durable compared to just a normal mirror itself. So that's why normally in modern technology itself, total internal reflection is used more often than not. And as well, because it's total internal reflection, because of the word total, right, all the lights will be reflected downwards. That may not be the case for a glass mirror, because sometimes glass mirrors do have a thick glass layer, which means you can actually have both reflection and refraction that takes place at the same time as well. Okay, but typically the most common example is actually use of optical fiber itself, because optical fiber is basically like this plastic or glass wire or strip that basically allows light to actually undergo TIR all the time. So when it undergoes TIR over here, I is greater than C, I and R will always be the same, and you keep doing this until you exit the over here. So this is like the signal. Okay, you send a signal there, and then this is the receiver. So basically, this is how we get our 5G or 6G data very, very fast, because instead of using electric wires that travel slower, we actually use light rays that move so fast. It's like in air, it is 3.0 times 10^8 meters per second, right? And even if you move it in glass itself, if you notice, we are using glass. So inside here, this is glass, and the outside here maybe is plastic itself. Okay, so basically why we use glass and plastic itself, so that we have total internal reflection. So therefore you can actually carry more information. It is lighter as well, because compared to metals, plastic and glass are definitely lighter and cheaper as well. And you can actually carry information faster and you have less signal loss because of all your TIR that occurs. So this is why optical fibers are generally better options than metal wires itself. However, because they're made of plastic and glass as well, this also means that they are also fragile. Now, for this part over here, the special device in this case, right? Because right now technology has actually advanced already, so we don't need to build newer special devices. We already got existing technology to do so itself. And unlike metals itself, metals we can just melt it and stick them together quite easily, right? Plastic and glass is not the case because usually for this kind of glass and plastic itself, they need to be very, very smooth and polished itself, which means that if you try to burn or melt them itself, they could actually become blurry, which is not good in that sense. Okay, so why do we use glass or plastic? Why not like other materials like water or whatsoever? Number one, because I have a large refractive index, this means that I have a small critical angle, and we are talking about chance. We are more likely for the angle of incidence to be greater than the critical angle. So if you are bigger than the critical angle, what happens? TIR can occur, and if TIR occurs, you have less signal loss. Okay, basically less light refract out of the optical fiber. So your handphone, when you play video games or when you watch your TV shows itself, they won't lag. Okay, they won't lag, they won't buffer. Now, why should we not bend the optical fiber itself? Because when the optical fibers is bent too much, the angle of incidence at the bend will be less than the critical angle. This means that the light signal or light rays will not undergo total internal reflection and instead will refract out of the optical fiber. This will result in signal loss. Okay, so basically this is what will happen. Now let me just do a quick sketch itself, so you can just imagine I have a very extreme bend like this. Okay, so what happens is if my light travels all the way to this point here, okay, all the way to the extreme, and when you draw your normal itself, you notice that the angle I is going to be less than C. So what will happen is that the light will actually go out and escape. Because the thing is, our our detector is over here. So if all the light rays, if you notice all the light rays like this or whatsoever, they all refract out. What happens? Basically, almost all of my light is refracted out. The only parts that can actually go to my detector is going to be less than optimal itself. So it's going to be very, very little light received. Okay, this is detector. I'm not sure why the spelling is not detect. Never mind, detector. Okay, sadly I don't know how to spell, but basically that's a detector itself. Okay, so that is how the light's supposed to reach the signal itself. So we cannot bend your optical fibers too much. We can only bend it slightly a little bit. Okay, if you bend it way too much itself, what happens is there will be signal loss. Why? Because your light rays do not undergo TIR, because angle of incidence is now less than critical angle. Remember, for TIR to occur, your angle of incidence must be greater than your critical angle. So in these cases, all of these, the angle of incidence is all greater than C itself. Okay, so to make things easier as well, we also use glass and plastic, because when you have a large refractive index, small critical angle, which means it's easier and more likely for any of my angle of incidence to be greater than critical angle, which means I can actually bend more, and therefore I wouldn't actually affect the signal loss as well. Because if I have a very small refractive index and a very large critical angle, it is less likely for my angle of incidence to be greater, right? So if I bend just a little bit, basically there will be refraction outwards already, which is not what we want.